Okay, so previously we had implemented a binary tree by defining a structure describing the components of each node. That is, each node had a value and each node had a left and right subtree pointer. And then we had a collection of interface functions that we defined for making binary trees, for accessing binary trees without changing anything in the tree, for modifying the elements in a binary tree without changing the shape. Now actually, if you think about it, for a binary tree, we did not implement any such functions, because if you start changing the values within the binary tree, you're very likely going to damage the ordering relationship. And then the fourth category of functions are the functions that do change the shape, and in particular we implemented a function that deleted the entire binary tree by first deleting the leaves recursively and then working all the way back up to the top. And actually that approach is pretty good, but it does have some problems. For one thing, there's no automatic initialization of binary trees. In order to get a binary tree, you had to declare a pointer to BT node variable, and then you had to initialize that by calling a make binary tree kind of function. That's really pretty clunky. We would rather be able to just declare binary tree objects and have them automatically be initialized as empty trees. The syntax of all this, that is the pointers to BT node structures, and in some cases passing copies of those, and in other cases passing addresses of those things into these interface functions, is pretty much of a mess for relatively inexperienced programmers. Part of what we would like to be able to do is to have our hard work be more accessible to less experienced programmers. The function names are sort of awful. We have things like make empty binary tree and binary tree delete and so forth. We'd rather just be able to have a binary tree object and say delete or copy with much simpler and less clunky names. Now, because an application developer knows what a BT node structure looks like, it's very easy for an application developer to wreck a tree. For example, an application developer could decide, hey, I'm done using this tree. Rather than calling this delete function, which seems like an awful lot of work, why don't I just assign a null pointer to my tree variable, to my header node, and not bother with the delete? Well, now the user has created a memory leak that an inexperienced user may not even know is a problem. We'd like to be able to assign one binary tree to another with a single equal sign. We'd like to be able to compare two binary trees for equality with the double equal sign and so forth. And we would also like to hide from our user, that is from an application developer, a lot of the internal implementation details of binary trees, so that we don't develop a collection of application developers who assume that our tree is implemented in some certain way, because in the future, we as the developers of the binary tree code might wish to improve it for efficiency or to save space or something like that. So we have a lot of issues here that we're going to solve by creating a binary tree class. That is, by making binary tree an actual honest-to-goodness data type. So first we have to talk about generally what a class is first, and then we'll get into the details of the binary tree class specifically. So what do we want classes for anyway? Well, the computer is designed to work with chars and ints and doubles and unsigned values. And in the good old days before classes, we as programmers usually had to think in terms of pushing our human level concepts like stocks, bonds, yield curves, and so forth down to this low machine level of the ints and the doubles and the arrays of doubles and so on. The idea of a class, which is a user-defined data type, is to bring the level of the language up to the level that we are conceptualizing our problem at. That is, Why don't we have a data type called stock, or a data type called bond, or a data type called yield curve that we can interact with in the way that we think of those things behaving in the real world? So that's one reason, is to lift the level of the language up to more closely match the problem that we're trying to solve. Another thing that classes give us, which gets us to object-oriented programming, is the idea of inheritance hierarchies. Using inheritance, we can express is a kind of relationships, which is both conceptually convenient and also turns out to save us a lot of awful copy and modifying kinds of coding. For example, if we can write some code describing generally what a call is, then a European call is simply a kind of call. Likewise, if we know what we need to implement to represent an employee, then we know that a manager is a kind of employee and a director is a kind of manager. So we don't have to redevelop from scratch everything about an employee just to implement a manager. We only need to implement the incremental differences between a manager and employee, and likewise the incremental differences between a director and a manager. Okay, somewhat more pragmatically, in terms of writing C++ code, what we want is a class that has a clear, coherent, and simple interface that is easy for application developers to use. Easier than dealing with header nodes and structure definitions and obnoxious long function names and pointers to header nodes and so forth. That is, we're going to make life easier for less experienced application developers by taking on the role of the more experienced class and library developers. Another important thing about classes is what's called information hiding. A class will reveal to its users details that the user must know, but also intentionally hides from the user things that the user should not know. This information hiding both prevents abuse of objects, for example, like I mentioned, of assigning 0 to a header node for a tree, and also prevents users from developing applications using internal details that they really shouldn't have access to. We will get both automatic initialization and automatic and correct destruction of objects. And in C++, it turns out we're going to be able to do what's called operator overloading, so that we can define how assignment works, so that we can define how an equality test works, so that we can define how the put-to operator works, so that we can display a binary tree to cout by just saying cout double less than, and then the name of our binary tree object. Okay, so here on slide 6 is the beginnings of how we define ourselves as a class. A class looks very much like a struct definition, except of course you use the word class instead. And in a class definition, we use what are called access control specifiers to separate things that are public, that is, things that can be viewed by application developers using the class, from things that are private, things that cannot be directly accessed by users of the class. The things that are private, the data that is private typically, can only be accessed directly within other code that belongs to this class. So here on slide 7, we have a really trivial example. X is our class that we're defining here. It has a public section and a private section. In the public section, we have what's called a data member. This is an int named I. In an application, if we create x1 as an object of type x, then we will be able to access the I data member of x1. I can say x1.I gets 123, and that will work just fine. On the other hand, j here is a private data member within x. So although I can see this class, and I can see that there's something called j in here, if I attempt to access j by saying x1.j, I get an error from the compiler telling me that I'm trying to access something within x1 that is private. Okay, now to be absolutely technical about it, a class and a struct in C++ are really exactly the same things. The only distinction is that in a class, you have to deliberately specify that certain things are public and other things are private. Whereas in a struct, everything is public by default. You can specify in a struct that certain things are private. And if you do that, in effect, your struct definition is interchangeable with a class definition. Stylistically, people tend to use structs, as I've indicated, as bags of data, whereas people use classes as higher level data types combining data which is private with member functions that users can call which are public. Okay, so in particular, the members that you can have within a class are in three categories. There are data members. These are variables that hold what we call state information. The second category of members are member functions that provide the interface that application developers use to interact with objects of the class. These member functions basically define the behaviors of the class or the services provided by the class. The third and less common type of member are member types. Sometimes a data type, that is, sometimes a class, may use internally a subtype as a convenience. For example, a binary tree class may make use of a BT node struct internally as a type to represent the individual nodes that make up the binary tree. Generally speaking, member functions provide the public interface to the class, and so member functions are usually in the public section of the class. Data members and member types, on the other hand, are generally private and only used internally by the implementations of the member functions themselves. All right, so here on slide 10, we have an example of a stock class. Now, every stock, we know, has a current price. If we want to be able to use stock objects in an application, we don't want the application itself to directly interact with that price variable. We don't want, if the price of a certain stock on a given day is 105, the application to say, oh, no, it's not, it's 80, and just assign an 80 into the price. All right, that doesn't make any sense. Even worse would be assigning a negative value into that price variable. So the price variable, the price member here, is private. Now, in order to find out about the price, or in order to change the price, we do have a couple of public member functions, setPrice and getPrice. All getPrice does is to return the current value of the price. So that's pretty trivial. Now, setPrice enforces some rules about what reasonable prices would be. If I attempt as an application developer to set a negative price for a stock, when I call setPrice, within the implementation of setPrice, we'll discover that the price I've requested is negative. The test is going to fail, and I'm going to drop down here to the else part and display this error message that I'm trying to set a negative price. But if the price that I've requested is valid, that is, if it's greater than or equal to 0, then I will set the price private data member within the current stock object to that argument value p. Each stock object will have its own price member, and notice that the two member functions have direct access to that price member. All right, so here on slide 11 is a brief little application program. I am declaring XYZ to be a stock object. That means XYZ has within it a price variable, and XYZ can be interacted with using these two public member functions, setPrice and getPrice. So if I say XYZ.getPrice, well, I don't yet in this stock class have something called a constructor. Therefore, when I declare that XYZ is an object of type stock that does allocate within that stock object space for a price, but it's uninitialized. So when I get the price the first time, I'm just going to get whatever garbage is sitting on the stack at the point where that stock object was created. Now I'm going to set the price. All right, so I say xyz dot set price, and because 47.12 is greater than or equal to 0, now the price data member is going to get that value, 47.12. Consequently, when I get the price again, I will get this 47.12 rather than garbage. If I attempt to set a negative price, then as we've seen, I get a runtime error. The program yells at me and says that I have a negative price. Or if I directly try to assign 9.25 to that price data member, that will be an error at compile time because it's an access violation. Okay, price is private within the stock class. The main function is not within the stock class. The main function is simply using stock objects, and therefore code in the main function cannot directly access that private data member price. Okay, so one of the things that we discovered with our trivial little stock class is that it started out by having an uninitialized price when we created the stock object XYZ. This really doesn't make any sense. So we're going to want to have something called a default constructor that will establish some kind of reasonable initial price for a stock. The default constructor is just one of what could be potentially many different constructors for the stock class. And the way you distinguish a constructor from other kinds of member functions in a class is that the constructor function name is the same as the class name. Now, this is to differentiate this from Python. If you create a class in Python, then there's one and only one constructor function called the __init___ function, right? But in C++, the name of the constructor is the same as the name of the class. All right, so here is a new and improved stock class. We still have our private price for the current stock object, and we still have the set price and get price member functions that behave in the same way as before. But now we have a default constructor. The default constructor name is the same as the name of the class, and it's called the default constructor because it does not receive any argument values. It is invoked automatically by default when you create a stock object in an application like main, or any other code that's not directly part of the stock class itself. Now, as it turns out, the New York Stock Exchange and NASDAQ won't list stocks whose prices fall below 1 for very long. So we are going to use a default of $1 as the price for any stock that we create. This is not extremely realistic, of course, but it's way better than having undefined price when we create a new stock object. Okay, so let's take a look at our application on slide 14. Now, when we declare that XYZ is a stock, memory gets allocated for XYZ. Within that memory is this price double, and that price double now is initialized to 1.0 by default rather than being uninitialized garbage. All right, so when I therefore call getPrice, what gets returned to me is 1.0. Now that displays as 1 because recall for floating point numbers that the trailing zeros are not displayed by default. I can set the price to a different value as long as that value is greater than or equal to 0. And then when I get the price, I will get that different value that I set. Okay, so this is the very simplest mechanism that we have for handling the uninitialized value problem. Now, when I simply say stock XYZ, or stock A, stock B, stock C, whatever, each of these stock objects comes into existence with some kind of valid default price. In the implementation here on slide 13, we did an assignment to the price data member of the value 1.1 in the body of the stock constructor code. But in general, for several reasons that we'll get to as we crunch along here, it's better to avoid assignment and instead use what's called member initialization syntax. Member initialization syntax is special to constructors. You can't use this with any other kind of function definition. Basically, you have your interface to the constructor, which is the name of the class with whatever arguments the constructor might take. For the default constructor, the argument list is always empty. Following that, you have a colon and then a list of the data members that exist within the class and initial values for those things in parentheses. And then following that member initialization list, you have your body of code. Now in this case, because all the body of code was doing before was assigning a value of 1.0 to the price, and I've taken care of that in my member initialization list, there's nothing left for the body to do, so the body is simply empty. It's fairly common, especially for default constructors, for the body of code to be empty, even though the body is nevertheless required. And furthermore, it turns out if you have a C++11 compliant compiler, you can use curly braces right in the declaration of the data member to specify the initial value that you want that data member to have. And in this case, since all I care about in my construction is that the price is set to 1.0 by default, now I can get away without even having a default constructor. I'll warn you, though, that I've encountered compilers that don't support this notation, even though they claim to be compliant with C++11. My own suggestion is that you get in the habit of using the member initialization list notation because that works for all compilers. You need it if you're doing inheritance, so it's probably the best and most reliable way to go.